So, welcome again to this talk on the impacts of climate change on butterflies and moths in the UK. My name is Simon Saville. I'm chair of the Surrey and South West London branch of Butterfly Conservation. I live here in London. Just to comment on the title slide here, the butterfly made from wild flowers with a card was given to me by a climate activist who had staying here, and I thought it was a nice indication of the fragility of nature and the interactions between nature. The stripes underneath are the warming stripes developed by a professor in Reading, and the time period they cover is one bar for each year from 1970 to 2020, I think, and it's based on the average temperature between those years, of all those years. And blue means colder than the average, and red means warmer than the average. And you can see as you go from left to right through the timeline that we get warmer and warmer and warmer. And all the hot years have been in the last couple of years. So this is what I'm going to cover today. We'll talk about the climate emergency. I'll assume people know mostly about that, so I won't spend very long. We'll discuss why Lepidoptera are good indicators. We'll look at changes in distribution. That's one of the most obvious things which is happening. We'll have a look at phonology. We'll go beyond averages into more local effects and micro effects. A couple of slides on what we can do and then draw some conclusions. And these two rather lovely comma butterflies were in Burgess Park earlier this year. Not often we see mating comma butterflies. First of all, the climate emergency. Two charts which should be relatively familiar to you. One on the left is the atmospheric CO2 in the Hawaii Observatory, showing the increase in parts per million. What's startling about this is that the rise has been relentless and been accelerating. It was going up at about 0.6 parts per million per year in the 60s, and that would quadruple to 2.3 parts per million per year in the 2010 to 2019 period. So the CO2 levels are just increasing despite everything we've been doing, despite all the 25 COPs that have preceded this one. On the right-hand side, you can see that the pandemic, this is a more recent 2016 to 2022 timeline, and there's no blip for the pandemic. People were hopeful that the pandemic would cause a blip, simply hasn't done so. So things are going on, and it's cause for great concern, I think. Then in August, we had the IPCC 6th assessment report based on the physical science. I think you'll be familiar that made it very clear that the human influence on the climate was unequivocal, no doubt about it anymore. They said in the report that temperatures will continue to rise until mid-century under all scenarios. Whatever we do, it's going to get warmer. And the UN Secretary General called it a code red for humanity. And as you can see, limiting to plus 1.5 degrees versus benchmark is almost unachievable. And based on the pre-COP nationally determined contributions, the temperature rise was predicted to be 2.7 if everything was done as promised on time. I think the latest idea is that will be now 2.4. Both numbers will be disastrous, of course. But it's not about the future, it's about it being here now. The left is taken from a poster, actually handed out by XR. They produced for some of the events in London. This is flooding like we haven't seen before in London in July this year. And on the right, of course, we've got the highest ever UK temperature 2 years ago in Cambridge, 38.7 degrees. So it's hot and it's getting hotter. So it's a cause for great concern, as I'm sure you're aware. So if that's the background of a rapidly warming climate, why are butterflies good indicators? Butterflies and moths good indicators. And the chart on the picture on the left, the small skipper and its range limits show one of the reasons why, and that's that a lot of butterflies and moths are at their climatic range margins in the UK. It means they're very sensitive to what happens at the local weather level. They're also cold-blooded. They can't easily control their own temperature. Some have some ability to have some influence, but it means they're very sensitive to what the outside temperature is. They also respond quickly because their reproductive rates are quite high, life cycle short, and they can disperse. So that means that they can move around the landscape, and we see them doing that. And importantly, they're very well studied. There's a long history of scientific studies of insects and butterflies and moths in particular. So they've got long-term distribution and abundance data. And here are 4 examples of data sets, 3 of them where butterfly conservation has a primary role, and the 4th one at Rothamsted. So in moths, 26 million records, butterflies in 2 different schemes, 15 million records in one, and 3,000 sites monitored in the other. And you can see the richness of data on the moth chart on the right-hand side. So a lot of data. So when we're looking at changes, we can be pretty sure that things are significant. I'm now moving on to distribution changes, and we'll talk through some winners and losers. The 4 species on the left-hand side here have been increasing their range, and we'll discuss some of the reasons why that might be, and show some of the really quite remarkable changes that have been going on. The ones on the right have been contracting their range sometimes, and in different ways, and we'll see some of those in more specific slides in a minute. So this is the comma. When I was growing up in Dorset, the comma was a special sight. We didn't see it so often, even though the chart here on the right-hand side of the screen shows that in the early part, the darker dots, it was well present in the south of England. But it was a good sight to see a comma. Now you see it much more commonly, and it's gone much further north. And since the 70s, it's moved more than 450 kilometers north at an astonishing rate of 11 kilometers per year. And in fact, it's been right up, I believe, to Dunnet Head, right in the north of Scotland there. Records were seen last year, I think it was. So the comma has become much more widespread. And one of the things which is, so the climate's clearly got more amenable for the butterfly, but it's been able to switch its food plants. So instead of just feeding on elms and hops, it now feeds on nettles as well. Nettles are much more widespread. So that availability of habitat, warmer weather, has enabled it to move north at a rapid rate. And it's become much more well distributed. The ringlet is another case in point. I was lucky enough to be able to take a cycle ride in this summer from Land's End to John O'Groats to raise money for butterfly conservation. I called it my bike for butterflies. And I went through Cumbria and Scotland, and I was chatting to the experts in both these areas. And they were saying to me that before, like 2014, 10 years ago, they almost never saw ringlets. They're unknown in their part of the world. And now, as I was cycling through, it was one of the commonest butterflies, and it's regularly one of the commonest species in the summer in Scotland. So that's moved north as well. The climate has helped. This ringlet, a bit tatty, was in a park in Glasgow, part of the Helping Hands project that Butterfly Conservation is running there to create wildflower meadows in parks in Scottish cities. But it was flying quite happily, and because it's relatively unpicky as to what its larvae feed on, it's able to move through the landscape quite easily. The brown argus is another interesting example. Historically, this was found on chalk grassland, caterpillars feeding on common rock rose. If you look at the darker colored dots on the map, you'll see that they essentially pick out the chalk and limestone landscapes of southern England and a few other places across the country. You can see the South Downs, the Chilterns, the Cotswolds, the Dorset, chalk and limestone ridges, etc. But since caterpillars started taking geranium species as well as common rock rose, it's been able to spread much more widely. And this once again indicates that you need the right climate and you need the availability of the right type of habitat. I was told when I previously used this picture in a slide, this is an aberration of a brown argus, but I haven't been able to find out which one. So if anybody knows what the ab is, then please let me know. And finally, I think on the butterflies, at least, the speckled wood, which you can see here, it's spread further than this. The orange dots are the spread and versus the darker colors earlier on. but the speckled is showing a lag, and it's quite common to have a lag between the climate change and species responses. So you have a climate which is suitable for the butterfly, but it's not present. And one of the reasons that's been found for this was habitat availability, and more suitable habitat available in Scotland versus Yorkshire. So more widespread in Scotland than in Yorkshire. So we're learning more and more. There's quite a lot of academic studies on this topic, or the topic of response to climate change, and it's quite an interesting area to study. Now on to moths. This is taken from the UK State of Moths report from Butterfly Conservation this year, and it's looking at 487 species of larger moth over a 20-year period. And where you can see the range margin changes on the bottom axis, and north is to the right. And you can see that the average northward shift by the red line is 5.1 kilometers per year. And the bars show individual species, numbers of species, and most of them are to the right of the datum line at 0. The dark colored ones are statistically significant. So a lot of data, you remember there was a lot of moth data available. So we're pretty clear that these things are happening. So 5.1 kilometers per year over 20 years is 100 kilometers. So these are big changes in moth distributions. And this example was in the same report, the State of UK's moths, about 4 species of footman. All 4 of these have spread further north from strongholds about 20 years ago. And interestingly, these are moths where the larvae feed on lichen and algae. And there's been although air quality isn't always great, lichen are doing better now than they used to be. The air is cleaner. And so this is not, the cleaner air is leading to more food plants. So the habitat is responding to the atmospheric air quality, as well as the butterflies to the moths to the temperature as well. It shows how complicated the interactions can be. But it's not all good news on distribution. This is the grey mountain carpet, which is a moth which likes a cooler, damper climate. And you can see here, the black dots are the current latest distribution, and the orange dots and light blue are the earlier. It's retreating north, it's retreating up to where it's cooler and damper. And the distribution has decreased by a massive 81% since 1970 time. So big changes, not always for the good. And now a mountain ringlet butterfly. It's our only really mountain species. It lives at altitudes of typically 450 meters or above in England, and 350 meters above in Scotland. I was lucky enough on my bike ride to see some at Ben Lawes National Nature Reserve, just next to Loch Tay. Fabulous place. But I was up at 450 meters to 600 meters above sea level to do that. But the chart on the left, which isn't very clear, I think, on the bottom axis, you've got elevation. So further to the right is higher elevation. And on the vertical axis, number of squares which are extinct, where extinction events have occurred for the mountain ringlet. And you can see it basically at lower elevations, greater levels of extinction than at higher elevations. So essentially this butterfly, is retreating to higher altitudes. And that's obvious that at some point there's nowhere left for it to go. And then it really struggles. So this is the butterfly which could really struggle if the climate continues to change. Now a much more commonly seen butterfly, or used to be commonly seen butterfly, the small tortoiseshell. We see very few second generation tortoiseshells in London. You know, it overwinters as an adult. Spring adults mate and lay eggs, and you see a second generation in the summer. We very rarely see those adults. And this is a hypothesis that I have, is more of a personal observation backed up by study by Malcolm Hull. You can see a link there. He's from Herts, Middlesex, Butterfly Conservation. He studied this in his own area and just north of London. But he's seeing that the small tortoiseshells and indeed the peacocks are going into hibernation earlier and earlier. And they're hibernating as early as July now. And I'm wondering whether this is an escape from warmer weather, because as I was cycling up through the country. Say in Carlisle, there was a roadside verge there that was teeming with small tortoiseshell. So they're not doing badly in some parts of the country. And I wonder, in Japan, the small tortoiseshell is an alpine species living at fairly high altitudes. I'm wondering whether that's simply it just doesn't like the warm weather, and the cold adapted species, and they hide away. These peacocks on the right were hibernating on a pillbox on the North Downs in August, like 2 years ago. That's again, I think it's fairly early in August too. So pretty early for hibernation to start. Now we're going to talk about abundance and distribution. If I look at the literature, there's quite a few papers that talk about high correlations between abundance and distribution. So if you get increasing abundance, you get increasing distribution, and increasing distribution, you get increasing abundance. But that's not always true. And I think that link may be broken more now than it was in the past, perhaps. This data is for 104 moth species from the Atlas of Britain's and Ireland's Larger Moths, which BC published 2 years ago. It's a fantastic book about our moth fauna. And you can see here I plotted distribution on the horizontal axis and abundance on the vertical axis. And essentially where you want to be is in the top right quadrant, where abundance is, the distribution is increasing and the abundance is increasing as well. But there's only roughly a fifth of the species that were studied, for which data was available in that quadrant. Most species are declining in abundance, 3/4 of the number, 4/5 are declining in abundance, although 1/4 are increasing in distribution. But worryingly, 58 of the 104, so over half, are declining in both distribution and abundance. So that's what you would call the extinction quadrant. So it's sometimes hard to get your head around that increasing distribution isn't always the good news you think it might be. We've got increasing distribution, but because we've got land use changes, pesticides, availability of habitat being limited, etc., abundance is not necessarily increasing at the same time. And to complicate the dynamic picture, we've got a lot of new arrivals to Britain. These are most of the new arrivals are moths, which we'll discuss here. And remarkably, since 1900, in 120 years, 137 moth species have become established and 51 have gone extinct. So that's quite a big change in the picture for moths in this country. And even in the last 20 years, since 2000, 53 species have arrived or returned to the country. Some of those have come naturally, of course, but others have been unwittingly imported by our own hands. And 2 were causing a bit of trouble, certainly here in the London area. The box tree moth, picture on the top right, is a lovely moth. It's actually officially a micro moth, but that obviously feeds on box plants, and it came in on imported box plants, probably via the Netherlands, but from Southeast Asia, I'd imagine. First seen in Kent about 14 years ago. And you can see the sort of damage it does to box hedges there in the picture below, and that hedge had to be taken out. There are treatments for the larvae, but they are bacterial treatments which are not specific to this species, so they'll kill any larvae they come into contact with. So spraying is not good. And the second moth, this time from Europe, Central Europe, is the oak procession, which came in about the same time, seen in Southwest London 15 years ago. It's now recognized as being established in parts of southwest London. And DEFRA has a program to try and control this moth every year. It spends more than £1 million trying to control and monitor its spread. And all we see is that the moth continues to grow the distribution area every year. It's basically got an amenable climate, and it's got oak trees to feed on, and it can survive quite happily. We can talk about that more if people would like, but it's not really the subject of this talk. And on butterflies, we've got some possibly already current residents, maybe in the future. I just picked out 3. There were more I could have chosen. The long-tailed blue, it wasn't a very good year for them this year, I don't think. coming over from the continent, but some years we see a lot of seen, particularly in Sussex and some in Surrey. It feeds on everlasting pea, so there's no reason why it can't establish here, really. In the middle, the large tortoiseshell used to be a resident species, went extinct some years ago, and is now regularly seen as a migrant. There was one seen in near Croydon this year. I happened to miss it, but it was on a day when I was on the site near Croydon. And it's regularly seen on Portland Bill, and I believe there's a breeding colony there. Whether that's a result of a release or migration, I'm not quite sure. So that probably will become resident as well. And then the southern small white, which is already on the continent, pretty close to the channel, certainly in the Netherlands. It's spreading northwest at a pretty rapid rate, and I don't think the channel will prove to be much of a barrier to it, given the right weather patterns and airflows. And it will be over here. It may stay undetected for a while because it's quite difficult to tell apart from our own small white and other whites. So it's a dynamic picture. Now we're moving on to phenology. So when things appear, when in the year, and we'll talk about London's urban heat island and what impact that has. We'll talk about the citizen science program run by the Woodland Trust and CEH, Nature's Calendar. We'll talk about moths and the difference between single and multi-generational species, and talk about the development trap of trying to fit in an extra brood. But the picture on the right was taken by myself July last year on Cannon Hill Common, which is down southwest 20, southern London. But I'd never seen ripe blackberries on the 1st of July before. I'm normally accustomed to picking them when I was growing up in late August, September. So something was going wrong here. And this was, so all the bramble flowers had gone before the gatekeeper butterflies came out. And those of you who know your butterflies will know that the gatekeepers love to nectar on bramble. So mismatches between food plants and insects is a big issue that people worry about. Let's just mention the urban heat island effect in London, because it's sometimes surprising to realize how big this is. On the left-hand side, you've got a chart. It's a bit old. There's a map of London showing the temperature in central London versus the outskirts, and you can see just from the visual effect that it's 10 degrees warmer in London than it is at the outskirts. And we regularly see an urban heat island effect of 4 to 7 degrees. But that's not just during the day, it's overnight as well. And sometimes the warmer nights which have the bigger influence. If you look on the right, this is a car parked outside our house on the road. And this is what passes for a cold night in central London these days. It was -1. We had half a dozen nights when it went below 0 last winter. On this night, when it was -1 in London, it was -19 in Aviemore, I think. So very big differences. And London is quite a warm place now. This initiative, which was started by the Woodland Trust in partnership with UK CEH, looks at the average dates for events in the Nature's Calendar. So whether that's the first leaf, first flowers, insects being first recorded, whatever it might be, citizen scientists record those events and compare the dates are then compared from the averages versus 2001, which was the benchmark year. And negative numbers mean earlier events happening. And you can see that in general, most of these numbers are negative, and they're getting more negative. So the trend is clear. The phenology is changing, and you can go on its website and find some extra information and browse some papers, which is quite interesting. But those changes are manifest in moths, and this is data taken from the Moth Atlas again. 2 moths, the grey birch and the sharp-angled peacock, and the first one, which just has 1 generation, you can see its flight period, which is the dark bars, move forward by a week or more. And in the sharp-angled peacock, the first brood is moved forward, and the second brood has become second generation has become more prominent. So quite big changes in their phonology as a result of the climate. But some moths, some species also flying later. Ones that fly in the later part of the year are moving later because it's warmer in the later months. So there's 76 species were found to be flying later. It's nearly 20%. 13 of those at least 7 days later, and this is the pink-barred sallow showing a move of more than a week. This looks at the difference between single generation and multi-generation species. Richard, thank you. Yes, thank you. Difference between single generation and multi-generation. So univoltine 1 generation and multivoltine 2 generations per year. This is a paper by Callum McGregor, and it gets quite complicated. But Callum was one of the people who joined me on my ride as we were going through Preseath Common in the summer, which is the Butterfly Conservation Reserve for the silver-studded blue, which was a fabulous site, teeming with butterflies on a not very sunny day, it must be said. But it gets quite complicated. But if you look at the silver-studded blue on the left, which has just the 1 generation per year, the phenology is advancing. The middle chart here, phenology is advancing trend, but the abundance is declining, and the distribution is declining as well. On the right-hand side, the small blue, which has 2 generations, similarly advancing phenology, same sort of chart, but it's increasing its abundance and expanding its range, and the hypothesis is that that's due to a larger second brood. Now the wall brown, which is a well-known species for having had a very large change in distribution and abundance since the 70s. Used to be common when I was growing up in Dorset, and you can still see it there. When I go back down, I still see it, but it was once a very common farmland butterflies. But now, as you can see, these blue hollow empty dots where it's become extinct in the whole central part of southern Britain. It's now limited mainly to the coastal areas, and this is thought to be due to what's called the developmental trap. And this is from a paper by Hans van Dijk and some others in the Netherlands, and this is their chart. And the important thing about the wall brown is it overwinters as a caterpillar, but only as a 3rd instar larva. So it needs to shed its skin twice before it gets to the 3rd instar, and then it can go into diapause successfully. So in the north, where it's cooler, or in areas where it's cooler, it will have two broods, reach the 3rd instar, and overwinter successfully. In a warmer place, used to be in the south, the 3rd brood can be successful, get to the 3rd instar, and again overwinter. But if it isn't quite warm enough, it starts a 3rd brood, and that 3rd brood doesn't get to the right stage for overwintering, then that will fail, and you'll lose a lot of the individuals. And that was the theory for the wall brown, and you can see that happening for other species as well, where an extra brood, if you have a warm late summer, they try to put an extra brood in, and it fails, and the population crashes in the following year. So you need to understand the ecology of the species to understand how it interacts with changing local weather. But it's not just about the averages. And this picture is simply a cover of a book, and it's a thermal image, and you can see of a grassy area. You can see the difference in temperature, blue being cold and red being hot. We're not very familiar with this ourselves, but it's very obvious from pictures how different those local temperatures are. So we've got microclimates, we've got extreme weather events, whether that's dry or hot, or indeed rain, and we'll also talk about thermoregulation, which is what butterflies may do to react. First of all, microclimate. This is taken from one of my favorite sites, south of Croydon, called Hutchinson's Bank. It's a site managed by London Wildlife Trust, which is very good for butterflies, flowers, and lots of other wildlife as well, in fact. But you can appreciate here how, if the air temperature is, say, 20 or 25 degrees C, how the short grass will be at a different temperature, the grassy tussocks at a lower temperature, the bare ground at a higher temperature, scrubby areas, similarly low temperature, sheltered areas versus open areas. So the temperature variations in all those places will be quite large. And this is a deliberately created scrape of bare earth here for the butterflies that like a warm microclimate like the small blue, and it thrives on this side. So we don't appreciate those changes very much, but the butterflies certainly do. And this is a study that goes into more detail on that, based on an area in Sussex. And the maps here, just so you get your orientation, the 1 kilometer line is here. So these are about 10 or 15 kilometers across. And you can see there's some contouring here. But essentially, the researchers modeled the thermal quality of the habitat using thermal imaging and interpolation modeling, and did it up to a 5-meter resolution. So pretty fine detail, and did it at 2 different years, 18 years apart, 1982 and 2000. And the colors show the number of hours where the temperatures exceeded 25 degrees C, which is the threshold for activity for this butterfly. It'll only fly above 25 degrees C. And you can see in the top map, lots of areas there, and they're mostly marked blue, which means not many hours above 25, and very few areas with bold outlines, which is where the butterfly was observed, just a couple of places really. Fast forward 18 years, and 2 things have happened. You've got more orange and red in the pictures than before, and many more areas where the butterfly has colonized. So even a small butterfly like the silver-spotted skipper is able to colonize over reasonably large areas over reasonably short periods of time, in response to the microclimate, and the macro change in climate over this period was much less than the microclimate change which butterflies are reacting to. So it's all about microclimate. So is a changing climate then better for insects? We talked about hotter summers, warmer and wetter winters probably, but more extreme weather events, more heat waves, more droughts, more floods, more frequent and more severe. And the picture on the left is Burgess Park, August last year, showing it looking like a desert in the drought we had. And the chart on the right is taken from an article in British Wildlife magazine, the latest one, in fact, called Death by 100 Droughts. And it just maps the number of days of temperature over 27 degrees and shows that's increasing, show how that inflection point was in about 1960 when the temperature rises, we started to increase. Now let's look at the impact of climate extremes, heat, cold, or drought, rain, but we'll focus on temperature here, and it's complicated, I warn you, and it depends on the number of generations that the species have. But if you just look at what's in the red areas that I've highlighted, this is for adults and hibernating adults. And you've got on the left side here, number of species, percent of species affected, and whether it's positive or negative. So first we'll look at extreme heat, beneficial effects on adults, detrimental effects on hibernating adults. So they don't like it to be hot when they want to be hibernating. Suddenly extreme cold, bad for adults, good for hibernating adults. So the effects are complicated, but very clear to observe when you do the detailed studies. Now just a word on droughts. A couple of years, 1976 and 1995, which are the 2 droughts here marked on this Met Office chart. I put the red circles around those 2 years, which are real outliers in terms of drought. They correlate with substantial crashes in moth and butterfly species, and there's a paper reference there if you wanted to look at it. But this is taken on the right-hand side from the State of Butterflies report by Butterfly Conservation, and it looks at abundance indexes, and showing that from 76 to 77, there's more than 50% drop in abundance for all species. And then the species which are habitat specialists didn't recover, and the species which are more generalists were able to recover. So different ways of reacting to those extreme weather events. And this shows the 95 drought. This is from a different paper, effect on butterfly populations, 3 butterflies and drops of 50% or thereabouts in each case. So very significant effects of summer drought on subsequent years. And now I think just comparing habitat specialists who's often the larvae have particular requirements. We're looking at the interaction of climate change with other changes in land use, whether that's habitat loss or nitrogen deposition or pesticides or whatever else it might be. And the butterfly on the right is a high brown fritillary, which I saw in Cumbria, and it's struggling in parts of Cumbria because of the climate is okay, but the land use is changing and there's nitrogen deposition and it's getting too fertile, and grass is growing where there should be bare earth or bracken litter. So it's too cool for their caterpillars. That's really struggling as a result. What you're seeing here is complicated interactions between land use changes and climate changes on the butterfly and moth diversity. But the outcome of that, there's a couple of papers which refer to this, which both by butterfly conservation authors, but the conclusion seems to be that you end up with fewer species, and the ones which thrive best are the mobile and widespread habitat generalists, and the specialists lose out. So that could be where we're going. Just a word on thermoregulation, and a bit of a plug for Martin Warren's book, which came out a year ago. 3 different butterflies here and 3 different ways of basking to react to the temperature. Some butterflies, like the red admiral, bask with wings flat open. This enables them to capture the sun's rays very effectively, and these are often dark colored. Others, like the white butterflies, quite often hold their wings at angles. They're using it to reflect light off their wings rather than absorb it and bounce the rays onto their bodies like a solar panel, thermal solar. And other ones like the small heath or grayling or green hairstreak bask with the wings closed and then angle their bodies so that the wings are perpendicular to the sun. So they are quite smart in how they react to regulate their temperatures. Other butterflies, like the painted lady or red admiral, are able to shiver their flight muscles, which enables them to warm up, and this is an advantage. It means they can fly at lower temperatures, even when the sun's obscured, which enables it to fly further, of course. And we often see these butterflies doing that. And moths will do this as well to warm themselves up before they take off. Now we're coming on to the closing part of the talk about what we can do, or what the problem is. And this chart is intended to demonstrate why 1.5 degrees is such a challenging target to meet, and why we probably won't meet it. This is about the supply side. So where does the CO2 come from? And you can see this chart, which is taken from a blog by the climate change advisor for Shell. He's been studying this sort of stuff for a long time, showing that the annual CO2 emissions are about 42 gigatons a year, mostly fossil fuels, some from limestone, calcination of limestone for cement, and some from land use changes and deforestation. Those are the 3 biggies. Now the challenge here is that the science says that the remaining carbon budgets, the amount of carbon or CO2 we can emit to have just a 50-50 chance of staying below 1.5 is about 400 gigatons. And that's only for a 50-50 chance. And if we're emitting 42 gigatons a year, that means 10 years, roughly. So we need to get to net zero by the end of the decade. So the next five years or so are absolutely critical. And change is needed sooner rather than later. And change taken sooner has a bigger effect. Now, this second way of looking at the picture is the demand side, if you like. So our consumption, your consumption, my consumption, our carbon footprints. So what do we do that causes CO2 to be emitted? And the chart on the left comes from a website called carbon.place. It calculated the carbon footprints and how they're made up of local neighborhoods, going to about a number of 1,000 to 3,000 households. It's a fascinating thing, and it's the danger of it is you get sucked into studying it for a long time. But I've taken three locations. I've taken Dulwich, relatively affluent place in southwest London, SW9 further to the north, about 5 miles north of that, then a town like Dorking, just randomly chosen really. And it breaks down the carbon footprint into consumption of goods and services, flights, driving of cars and vans, gas and other heating, and then electricity. And the striking thing here is that in each case, the totals vary, but in each case, consumption of goods and services makes up more than half our carbon footprint. So what we do has a direct effect on how much carbon is emitted. So that's an important thing to remember. Similarly, a lot more flights in Dulwich than there are in Dorking, and so on. This third way of looking at it is a more integrated way. This comes from Bill Gates's book, How to Avoid a Climate Crisis, and it shows the sources of greenhouse gases, whether it's electricity or making things, or heating and cooling, traveling around, moving things around, or growing things. And you can see the big amounts of CO2 in each case. And I think the basic conclusion here is that we need to tackle all the sources of greenhouse gas. So that means everyone, that means individuals, governments, companies, need to do as much as possible, as soon as possible, everywhere across the world. And then we've got a chance. And that means supply side, how we create our energy, and demand side, what people do in terms of requesting and buying goods and services. And just to put this in context, the climate crisis and biodiversity crisis are two sides of the same coin, of course. And the agriculture is a very good example of that. 2/3 of the land in the UK is farmed, a third for crops and a third for grazing animals. And that's a very small part of our GDP, but a very big contribution to greenhouse gas emissions. And finally here, the Daz Gupta review, which came out from Professor Daz Gupta in February this year, was commissioned by the government. And he was making the point that our economies are embedded within nature, not external to it, that's contrary to what way you've been treating it, that our demands far exceed nature's capacity, and that we're endangering the prosperity of future generations. Remember, this is a government commissioned report, and that the GDP is a very bad way of measuring economic success. We need a way that includes sustainability, and that transformative change is possible, is one of the quotes he makes at the end. And I recall a remark made by Dave Goulson, the bumblebee expert, who said that parents will do almost anything for their children except bequeath them a planet that's safe to live on, which I thought was quite telling. Now, just in conclusion, I hope I've convinced you that it's getting hotter, but we'll have more floods and more droughts, but it's also happening now. It's a complex picture. There are arrivals and extinctions, both locally and nationally. There are range expansions and contractions. It gets complicated with effects of when land use changes and habitat availability are combined with climate changes. Phonological effects are very significant, but that can be different on different life stages of insects. Microclimate and microhabitat are both important, and extreme weather events are going to be more and more significant. And it looks like we're going to have a future dominated by fewer species, but with the more mobile and widespread habitat generators as doing better than the specialists. And as Dan Hall, the director of conservation at Butterfly Conservation, wrote in the magazine in the spring, the impacts of climate change on butterflies and moths are rapid, varied, and unpredictable. So we need to do everything we can to limit climate change, and that's certainly true. Quickly wanted to acknowledge the various people that I've called on for information for this talk, particularly Richard Fox's presentation at the annual general meeting last year, which is available on YouTube, which has a lot of the source material in it. Similarly, a presentation by Marcus Rhodes from an FSC arranged event, Some Like It Hot. That's also available on YouTube, and you can see the other people there. Thanks to everybody. Now, one shameless plug. I'm afraid, for my Bike for Butterflies. The sponsored ride I did from Land's End to John O'Groats, just 1,200 miles in 30 days, and was supported by lots of fabulous people on the way. And I visited as many reserves as I could, raised publicity, bring attention to the plight of the environment, raised well over £30,000, so pretty pleased with that. But if anybody is motivated and enjoy the talk, you can still donate at that link. Just go to Just Giving and write in Bike for Butterflies and you'll find it, or go to this Bike for Butterflies website. Thank you. That concludes my talk.